Okay, I hope you can see this.
Yes, sir, your screen is visible and you're audible.
Okay, good, good. So before we start talking about processors, because this course is about processor, I would like you to concentrate on this Snapdragon processor, which is showed over here. I'm sorry, it is known as Snapdragon System on a Chip. Now you'll see over here that this is CPU. And we'll keep on talking about this. But as you can see in a system on a chip, there are a lot of other things, other processors, which we don't consider when we talk of CPU. So CPU, as an old name that suggests central processing unit. So this is like a manager of the whole CPU. It would direct each one of these processors to work. It will divide up the work between GPU. It will divide up the work with DSP. This is a standalone connectivity, which is known as baseband chip. So it will connect to your LTE, Wi-Fi, so various. Now it is also 5G. It will connect to Wi-Fi. The latest Wi-Fi standard is Wi-Fi 6, USB, various Bluetooth and FM. There is a special multimedia thing. So again, audio, video, and gestures recognition. And there is a camera chip. So all your AI things are done over here. This is a special chip for which handles your display and LCD, and this is for navigation. So where you have your GPS, 6-axis sensors, etc. So we will be concentrating on just the CPU in this particular course. I'll keep on referring to GPU and DSP as I have done in previous lectures. We are not going to talk about baseband thing. This baseband thing, you are going to learn about in your coursework in signals and systems and other things, how these protocols work. So this one has CPU or a processor. This is a processor. This is a processor. This is also a processor. So everything is a processor in here, except that this CPU is a general purpose thing, and rest of them have a specific purpose. Now, let us go to the next slide. Now, in this particular course, we are going to break down this course into two parts. So the first part, where we will talk about ARM architecture, it will be known as a programmer's view. And the second part, where we talk about the implementation in detail, that means we will talk about number of pipeline stages, how they interact with each other. If we increase the number of stages, what would happen? If we decrease the number of stages, what would happen? All those things are part of implementation. I would like to give this analogy between a car driver and a car mechanic or an automobile engineer. To drive a car, you don't have to be automobile engineer, right? All you need to know is know a little bit about steering, know about how the brake works, how the accelerator works, what's the function of a clutch, then handbrake, signals, wiper, etc. And you are done. You don't have to know anything what is under the hood, or how does a car starts when you turn on the key, or what happens when you change the gear. Right, so as a simple driver, you don't care. I mean, anything may happen. So very similar to it is a programmer's view. When you write a C program on your laptop, do you really care what kind of processor is there in your laptop? It could be AMD processor, it could be Intel, or nowadays it could be even ARM processor. You don't know how many pipeline stages are there in the processor. For you, that is like, something under the hood of a car. You don't care about those machines. So that is a programmer's view. So programmer is interested only three things. The first one is instruction set architecture. And I will come to that, what that instruction set architecture is. Second is number of registers. Third one is interrupt model. And the fourth one, which is not written over here, is memory. Okay. So now, now this is a good time to discuss exactly what do you mean by architecture. I hope you can decipher my handwriting. I'm still not come to grips with this pen, but I hope it's readable to you. Now, architecture has got list of instructions. Now, what are these instructions? Let's say you have made a computer, just like Turing and his team did at Bletchley Park. Now you have got some nice hardware. So, you prepared this hardware. And as programmer's view goes, I don't know what is inside, but it is some, you may call it computer. Now, my question to you would be, what can it do? So then, you say list of instructions, say, okay, this computer can add two numbers. So there is an add instruction. You can say that it can subtract. So there's a subtract instruction. You say that, in my program, branch instructions are very important. Like, when you write a C program, if then else or a case statement or a do while, they are all branch statements that determine the program flow, whether it will take this branch or the other branch. So, you have some kind of branch statement. It could be unconditional branch or conditional branch. Most of the branches, as you know, are conditional, like, if then else is a conditional branch. If your termination condition is not met, then you branch. If it is met, then you don't branch and go out. So there is this branch type of instruction. Then there are or means logical instructions, so or and so on and so forth. We'll talk about this in much more detail, but this is a list of things which my computer can do. It should be able to do. So when I say add, I should be able to put in two numbers, that is number 1 and number 2, and the output should come out here, right? So this is what I want, and then this is the number of instructions I write. So now this is very important for a programmer. Right? Just like when you are learning a C language, you want to know structure of C language. That how many instructions are there, if then else, if it is there or not. Then you want to know whether the pointers are there or not, do while is there or not. How do you use a case statement? So very similarly, one step lower to C level language is assembly language. So this is your assembly language. Now, when you say add, it is all well and good, but how do you tell computer what is add? Now, your computer understands only 0, only 0 or 1. So that means it speaks only binary language. So when it speaks binary language, you have to feed So you have to tell your computer in some binary word. Now, usually computers modern computers have either 32-bit or 64-bit system. So what it means is that one instruction, so instruction like add, will have 32 bits of information. So when you say add two numbers and put the result in third number, now this kind of description is easy for humans to understand, right? Add, we all know what add is because it's in English. So we understand what add is. Then, this is the first number, this is the second number, and the result you want to put it in the third number. So it is very logical to us. But computer doesn't understand this. So you have to decide that, for me, add would mean 0, 1, 1, 0, 0. Let's suppose this means add. Then, you put in two numbers and then, you put the result in the third number. So this is 0, 1, 0, 1, 1. And then, the final number. So this would make a 32-bit instruction with all zeros and ones. So computer understands this very well. So this is known as the most basic language a computer understands. A level higher to it is this assembly language, and a level beyond assembly language is your programming language like C. And within programming languages, C is considered as the bottommost language. Bottommost language is not a bad word. Bottommost language means sometimes it is good that you can actually touch the hardware and make it do something. Whereas languages like Python and Java, which are interpreted languages, they are considered still higher order languages. So this is how the structure goes. This is programming language, then assembly language, and binary language. Okay. Binary language is great for computers, but bad for us. If someone tells me 001110 and speaks that language, I would not understand what that person is trying to tell me. If someone tells me add this number, and this number, I would immediately understand it. So assembly language is mainly made for humans. So anything about this is made for people like us, and binary language is made for computer. But you must realize that everything, if you want to solve it on your computer, it has to be finally converted into zeros and ones. Now, if you want to tie it up with your basic electronics subject, usually now, the chips have like 1 volt. And, you decide that any voltage level between 0 to 0.3 will be considered as logic 0. And 1 to, let's say, 0.6 is logic 1. This is logic 1. And anything in between is what we call it as indeterminate. So, I mean, if your logic level, voltage level falls here, it would be called a Z state. It would be considered not as 0 or 1. And in fact, it is a bad thing if your signal level falls here. So this is how your programming would work. Now, let us go. So this is, we are talking about instruction set architecture. We have understood. So instruction set architecture is, I have got this number of instructions which say add, subtract, branch, and or. I mean, yeah, there are like 56 of them in version 4T. So if you look at your book of ARM architecture, it has got 56 instructions. And using this 56 instructions like bricks, you can make a huge palace. Just like, in C language, there are few constructs, if then else, do while, case, and, a few more and some few data types, some data structure. And that's about it. Using this thing, you can write the most complicated programs or most complicated operating system. So Linux is written purely in C, right? And C has got just few constructs, and based on that and using them in a nice way, you can write a huge program. So similarly, in instruction set architecture, I mean, 56 instructions are given over here in your book in what we call as ARM version 4T. Number I will explain to you later. But that has got 56 such instructions, and using them in various order and judiciously and logically, you will be able to write a program. You can write a merge sort program. You can find a program which can detect a palindrome. So, whatever you were able to do in C language, you should be able to do in assembly language. The thing is that, if you are a good assembly language programmer, you can write a program which can execute much faster than a C language, right? So there is way of mixing up assembly language and C language programs together, which you will understand when you do your labs. That you want to write a small subroutine, and the whole program is in C, but you want to write a small subroutine in assembly language. Why? Because probably you want to know the 26th bit of a 32-bit number which is stored in a computer memory. You cannot do it using a C construct, because C construct does not give you a freedom to find out what is the 26th bit in a 32-bit number, but assembly language can. So in lot of audio thing, where you want to know what is the status of the 26th bit, and whether it is 0 or 1 has a significant meaning. For those things, small modules or subroutines are written in assembly language. Okay, so we first figured out what an assembly language is. Then, what more do we have? Then, we have something we call as registers. So the second word, it says registers. Now, what is a register? So in your, I just want to ask you a question. Were you taught what a register is in your DLD class? Can someone answer, please?
Yes, sir.
Yes, sir.
Okay. So register is nothing but a collection of flip-flops. So if you put 32 flip-flops together, it will make one register in ARM processor, which we are trying to talk about. Some of the higher-end ARM processors are 64-bit, but we are not talking about those. So you have certain number of registers. So how many registers are there in ARM architecture? We will see that an ARM architecture has got total 17 registers which are visible. To the programmer. And rest of the registers are useful only when there is an interrupt. I will tell you what an interrupt is a little later. So, and you will start scratching your head. I may say that there are 37 registers in ARM architecture, out of which only 17 are visible to the programmer. And you will start wondering, so what does that mean? Well, it is just like in your car, there are so many processors, but they're embedded. You don't know. Only car system uses it and then gives you an answer in some way. You are not directly interacting with those processors which are, say, ABS or your airbags or fuel injection system. You don't communicate with them. They just give you the answer to some main processor block which displays it on your dashboard. Similarly, 17 registers are visible to the programmer. Now, why is it important for a programmer to know how many registers are there? Well, the structure of an instruction actually is like this. Add register R1, content of the register R1 with content of register R2 and put the result in register R3. So this is different than the value which I used to put in the previous slide when I gave you an example. Here, this way of writing is much better because the value of R1 and R2 may keep on changing. Right? You're writing a program and then, your next line of code would be, say, increment R1 by R1 plus 1. And then, also increment R2 by R2 plus 1. And then there is a loop. If instead of R1, if I had put the actual number, I will have to keep on changing the statement every time. Whereas here, you just give the name of the register. So your computer understands that when you have written add R1, R2, R3, means the computer will understand, of course, there will be a kind of a compiler which compiles this program into a 32-bit ones and zeros so that the hardware of the computer knows, oh, this means add. First 5 letters are for instruction. So 110001 means add, just for example. Then it says, okay, R1, that means the content of R1 I have to take. Then R2 means content of register R2 I have to take. I have to add them up together and put the result into register R3. Is this clear to everyone? If you have any questions, please ask me now, because the concept of register and instructions is important to understand. Okay, if there are no questions, then I will move.
Sir, could you explain it one more time? I didn't understand the first one.
Okay. So this add R1, R2, R3. This example, right?
Yes, sir.
Okay. Say, I've got this machinery. Let me just draw this a little more clearly. So my hardware would be something like this. This is my computer. So this is my hardware. I would like to throw in an instruction which says add R1, R2, R3. When this instruction goes inside the computer, what is inside the computer? I think I should draw this figure. Inside the computer, I have this ALU. You know what ALU is, right? Arithmetic Logic Unit. Are you aware of ALU?
Yes, sir.
Okay. So here's my ALU. And here's my register file, which has got register R0, R1, R2, R3, up to R17. So there are starts from 0 to R16, R0 to R16. When it sees, it decodes. I mean, of course, when this goes in, it is in ones and zeros. But this ALU will be decoding that, what this number means, what add means. And ALU can do multiple things. But, when it sees this add, it knows that, it has to add the values of these two registers. So when it sees R1, it fetches the content of register R1 and puts it as an input, first input. Then it reads R2. So it goes and reads register R2 and put this as a second source operand. And the output which comes out, that means the addition of the content of register R1 and content of register R2, it will store it into register R3. So this is how your add R1, R2, R3 would work. I was just implying that writing this way, add R1, R2, R3 is much better than, writing add, then, one number, then another number, and then location. Because writing things in terms of variables is always better, because otherwise you won't be able to write a program in a loop. So R1 sort of is the name of a register. So I say add register R1 means what I'm actually trying to tell you is add R1 and R2 means add the content of register R1 to the content of register R2 and store it in register R3. Is this clear?
Yes.
Yeah.
Sir, can't we do that after adding R1 and R2, we store the result in R1 only? In that way, the number of register used will be less.
Okay. So that depends on the hardware design. You may want to keep the value of R1 as constant, right? And you don't want to change the value of register R1. So in C language, you have something like R1 gets R1 plus 1, right? So here it all depends, because this is a lower level thing. And you have to actually worry about that, are you going to overwrite the result when you do this? So you want to do it in a second step. So you will see when you do the examples in assembly language programming, you will figure out whether it is doable or not. Okay.
Okay.
So do some examples. Soon, your lab sessions would start. Your TAs have been assigned. Probably from next week, we will start having our lab sessions. So when you do start writing programs, probably you will realize whether you will be able to do that or not. Okay, so we have talked about first thing that, in a programmer's view, knowing what kind of instructions are there is important. That is number one, and we figured out what are the instructions over here. I wrote add, subtract, then multiply, and it could be so. Then there are logical instructions like add, and, or, not. Then there are say branch instructions, so like branch conditionally, branch unconditionally, etc. So these are all instructions. So a programmer needs to know how many instructions are there, and I'm telling you in advance that the assembly language which you are going to study has got 56 such instructions. Okay, that is number one part is clear. Part number two is how many registers are there? Now, why is it important? Well, it is important, because can I write, say, an instruction like add R19, R20, R21? Well, obviously I can't. And why I can't do that? Because, those registers are not defined. Those registers physically are not there. So As a programmer, I need to be told how many registers are there. We'll also see that, when I say there are 17 registers in ARM, not all the registers can be used. Not all the registers can be used. There are some special purpose registers, which I will tell you a little later. So now we also understood the importance of knowing how many registers are there, because only then we can write a program. Otherwise, you can write a program like this. You may think that, okay, it is what's wrong, it is syntactically, it is correct. But then there is no R819, there is no R20, there is no R21. It does not exist. So second thing is also clear. Third thing, interrupt. Now, phenomena of interrupt this is very important for us to understand. Why interrupts are important, and first of all, what is an interrupt? Let's say this is your processor, and this could be part of your laptop, and your user program is running. Now your user program may be a class assignment. You have to write a program in C language, whatever language. So you have given it the command. Now at the same time, you are using your mouse, right? You are typing something. Now there is no magic. How would your laptop's processor understand that you are typing something, or you are clicking your mouse, or at the same time in the background you are downloading some music or some lecture file? I hope you are downloading lecture file and not music. But anyway, those things are also running simultaneously. So what happens every time you hit the keyboard? When you hit a keyboard, or say A, or you want to type character A, when you hit that particular key, it goes to the processor and says, there is something I want you to register, that a user has typed a character A. So what processor has to do is stop executing the user program, take notice of that interrupt which has been sent. Interrupt is nothing but a signal which is sent by external devices. External devices are like keyboard, your mouse, or something which is downloading, something which is coming through your USB, something which is coming through HDMI. So these are all external signals. So it's like, you are studying and other people may knock your door, or may give you a phone call, or, whatever way, to get your attention. You are doing studying, and, there are external people are trying various ways to communicate with you. So they are known as interrupt signals, and they could be of different types. So just like in our case example for humans, it could be a phone call, it could be a WhatsApp message, it could be an SMS, or someone actually knocking on the door, ringing the bell, or if it is your mom or dad, then shouting your name. These are all interrupt signals. So very similarly, for a processor, the interrupt signals are coming from external devices like your keyboard, mouse, HDMI cable, USB cable, something which is downloading in the background. Every time your processor will have to stop what it is doing and then service that interrupt and again go back to user program. Now, this sounds like a complicated thing that, if my C program is executing, I don't feel that, the program is getting slower. Well, that's because your processor is very powerful. It can do billion operations in 1 second. So even your keystroke would be, registered in less than 0.1 microsecond. And you won't even realize that, the computer took an interrupt, it stopped working on your program, it did something else and again came back. Yes, when you are downloading a huge video file, you may find that, your computer has become slightly sluggish. And that is possible because, your processor has to be interrupted many times. And when it is downloading something, it has to be really paying attention to the file which is downloading. Otherwise, if it misses out on downloading it, then, it may miss out some bytes and your file may be corrupted. So this is the concept of interrupt.
Sir,
Yes.
so what does it mean when we call file as a corrupted? Means what is corrupted?
Well, corrupted means some of the bytes were not downloaded. So, if it is a picture, you are talking about, then, picture may have some gaps or it is pixelated or, there are some bits which are missing and, certain words are missing. So, I mean, there are many meaning of corruption of a file. Some file may be genuinely corrupted because sectors are bad. But basically what it means is, suppose it has to have a million zeros and ones, and each pair of 8 means a character that, I mean, that, for character A, it's an 8-bit thing. And then every character is given an 8-bit binary number to correspond to a particular character. Now, some of these characters are not downloaded or, your computer missed out or buffer was full and, it got spilled over or, so then, your file which comes, might be missing some words or picture if it is being downloaded might be missing some pixels and the overall effect is not good. Is it clear?
Yes, sir.
Just a small doubt in the ALU. In ALU, if it is computing something, for example, the addition, then would there be a similar register kind of thing which would be storing the answer in the ALU?
Okay, I mean, we are going to talk about this in implementation, till we, in fact, for the almost whole of semester. But, to give you an advanced idea, your processor is usually designed like this. For a very simple 3-stage, there's a fetch stage, there is a decode stage, and then there is the execute stage. Your ALU resides here. So execute stage has your ALU. This is your memory. And memory have instruction. This is your instructions. So all your program that you write, like add, then subtract, whatever you write will be stored here. And the data would be stored over here. And this is your common register file. This is known as instruction memory. This is known as data memory. And this is known as register file. Okay, I'm going a little ahead of this course, but I think it is good to have this idea in your head. Now, register is the fastest memory. Why? Because it is part of the processor. So if you put, I mean, in a way, all these are memories. Register is a memory, data memory is a memory, and instruction memory is also a memory. But there is a difference in terms of speed. So registers are right there on the die with the CPU. So registers are the fastest. And of course, it's the most precious because, it has got only so many registers in a processor, say 16 or 17, as we talked about in ARM architecture. Instruction memory could be 1 MB or, data memory could be 1 MB, 2 MB. And then your RAM could be a few GB and so on. So anything which is in register is very quickly accessible by computer. But you must remember you have only 16 spaces. And I think you asked this question, so I want to put a seed in you guys in your head. What would you put in your register file? Say I would put in my register file some variables which are used again and again. So if I say that if I'm writing a program which says for I equal to 0, I plus plus till I equal to 100. Something like this. It's a pseudo instruction. So let's say my counter, I would like to put this value in, say, one of the registers, R1. And I would like to keep it there. Why? Because in my program loop, every time it wants to check the termination condition. So I would start with the value of I in R1, and then, I would have update R1 gets R1 plus 1. And then I would check whether R1 is equal to 100 or not. And then if not, then, go and do this sum operation again. So for these kind of thing, I would like to keep my R1, my value of this I into register file. But there are other variables which are seldom used. I don't want to keep them in register file. They would be lying in data memory. Someone has asked me what's the difference between cache and register. So first of all, I would start with saying similarity. Cache is part of instruction memory and data memory, right? There's a data cache and instruction cache. And this is register. Registers are very precious. Very small number, just 16 words. And actual usable ones are even less because some registers are assigned to some specific things. So general purpose registers are only 13. Whereas data cache and instruction cache, that means which is nothing but part of instruction memory system and data memory system. Those things could be in terms of kilobytes or megabytes. All of them are memory, so that means they can all store a 32-bit number. But this being the fastest, the access speed is the fastest over here. Whereas here only in the first level cache, it is good. That means as fast as processor, but otherwise, it is much slower than processor. So sometimes you have to waste 10 cycles or more in accessing data from this. So if you want to, at this moment, if you want to understand, assume that registers is the fastest memory ever in your whole computer system. And your computer memory system consisting of your secondary memory, that means your hard drive, your RAM, then various levels of cache and registers. They all form a memory system, right? What is the purpose of a memory system? It stores various memory or various things which you might need. Your secondary memory, that means your hard drive may have 1 terabyte worth of things. But your registers would have only 16 words. And so that means very, very low. But it is the fastest. Your hard drive is the slowest. Accessing your hard drive takes times in terms of milliseconds. Whereas accessing your register is done in nanoseconds. Right? So that is the difference. Basically, they're all memory, but the difference is in terms of access speed and size. Is that clear?
Yes, sir. But means my question was that does the ALU also have a register or something other memory form where it temporarily stores the result?
Okay, good question. We will come down to something which is known as RISC versus CISC when we talk about ARM architecture. ARM is using a RISC architecture. Now, the RISC architecture is not the same as RISC-V. RISC means reduced instruction set computation or computer. If you don't want to get too much into it, then forget what I just said. In ARM processor, my processor can only deal with registers. It can accept the value from register and it can put the value in register. It cannot directly communicate with instruction memory or data memory. That is a major difference. So if you want to calculate some value of R1, R2, R3, and value of that, what you want is not in the register file, you will have to first get it from data memory, put it into register, and then only ALU can use it. So in other words, ALU will communicate only with register file. So it can use only R0 to R13, R14, 15, and 16, as you'll see that, they are different, used for different purpose.
Sir,
Yes.
sir, if a register cannot read the memory from the things from a RAM, then how can we input the data into the registers?
Okay. Register and, the data flow between memory systems starting from hard drive, going through RAM, then going through your cache system, and then register, data can flow. So if the data, because, as you know, that register can have only 16 words, whereas your program might be, 100,000 lines long. So then, it is known as memory management, that, at the right time, you want to bring in the right memory into, finally, it has to be brought into register file. Now, it is the art which is used by your operating system of what data or what instruction to bring in. So basically, your register file would maintain data that you are using. So your instruction memory, or sorry, your data memory and register file can communicate. But ALU can communicate only with register file. It will not communicate with data memory.
Okay, sir. And sir, one more thing.
Just 1 second. I made this RISC and CISC. I was just trying to discuss this because in Intel architecture, you can add content of a register with content of memory, right? So you can say add register R1 with content of a particular address of data memory and put the result into directly data memory. That means put it in the cache. That is very complicated. So all the new processors which are coming out, they are of a simple type. And simplicity is ALU will talk only with register file. Now, register file may talk with your data memory, and data memory can talk with various levels, L1, L2, L3 cache, goes down to RAM, and then goes down to your hard drive. That is all allowed. But ALU recognizes only register file, nothing else. And this concept should be very, very clear in your head, everyone's head, that ALU deals only with register file. Register file can deal with, your data memory and, lower levels of various memories, but not ALU. ALU will takes its operands only from register file and put the result only into register file. So you will see there are instructions like load, which is like LDA, and store.
Sir?
Yes.
Sir, when we turn off the computer, everything inside the RAM and the cache memory got erased.
Say that again. I'm sorry, I didn't get your point.
When we turn off the computer, the memory which is stored inside the RAM totally got erased, means everything becomes zero.
Okay. I don't know whether we want to go into memory because, memory is one of the most important part of this coursework. And, it comes into implementation part. So if I discuss it too much, we will be jumping way far ahead of the course. But, for your satisfaction, let me just discuss, this is, if you don't understand at this point, I think you should understand what's the point. This is, say, register file. This is your L1 cache for data memory. This is L2 cache. And some places even have L3 cache, so increasing in size. Then, you have got your RAM, which is much bigger than this. This is your RAM. And this is your, assume it's a very, very big thing in hard drive. Now, as you see that, the size of the memory becomes increasingly smaller when you go this way. The speed becomes increasingly faster. When I say speed, means access speed by processor. So here it is the fastest. When it is in register, because it is right there next to ALU. So ALU will have no problem accepting the values and putting the values back in. Whereas these ones are slower than this. And this is like very, very slow. This is might be like, 10,000 times or 100,000 times slower than your register file. Now, as you can see, when various programs are being executed, these values would be erased, right? When the value is erased, and then, suppose you need it again, like, your user program, and, you will encounter it many times. Your user program is running. And then suddenly some interrupt has come, and, interrupt is nothing but another program. So suppose handling your keystroke requires a program, right? Where to place it, how to store it, or what to do with it, or downloading, it has to be a program where, it instructs your processor where to send the data, how to store it, whatever. So suppose this is the data which has been wiped out because, something else had to be put in over here. When you want to restart this, then, you have to go to lower levels of the memory. If it is lost from everywhere, it must remain into hard drive. I mean, of course, it will take a lot of time to bring stuff from here to here. When I say lot of time is a sort of a relative term. It may take milliseconds to get data from hard drive to your processor. This is your ALU. So it may take a lot of time to get jumping through here, from here to here, here to here, here, and then here. So as I was saying, ALU deals only with register. It takes values from the register, puts the value back into register. That's it. ALU doesn't know this. Whereas register, there is a memory controller, which is something like this. It sees that, the data which was wiped out is again refreshed whenever it is needed. So this is how it works. So when you say that, if something is wiped out because, the size is small and, another program was executed, where will it be replenished? Well, it will not be removed from hard drive, right? Hard drive is way too big. It has got everything in it. So then, things would start jumping back and, you have to refresh it. Does that answer your question?
Yes, sir.
Okay, so I mean, this is we are getting ahead of our point. Memory system is a very important thing to understand, but let's not worry too much about it as of now. So we have understood one important thing, that there is this register file. So it is important to know register. And then, finally we learned about interrupts, that, interrupts are important, and interrupts are the ones, which is coming from external devices, which would tell your program which would tell your processor to stop executing user program. User program might be your program. You are the user. So you have written C program, and at the same time, you're typing something. Your C program is being executed. You may not write a very big C program that, you have a chance to do typing, because, your program might be executed in just few milliseconds. But, let's say you have written a 100,000 or 1 million line C program. By the time it is executed, if you are typing something in some other window, or you are downloading something, interrupts would be constantly going in. And I'll also give you an example. Some people have a bad habit of shaking their mouse while they are doing something. It is out of, it's a tick. Very bad thing to do. I mean, you are slowing down your computer by constantly, shaking your mouse like this. It might be a tick on your part, or you are anxiously waiting for a result to come out. When you do this, you are interrupting your processor. Your processor may say, okay, the user is trying to tell me something. He has moved the mouse. But, what does it mean? Nothing. You are not clicking. So it says, okay, no signal. I will go back to my work. Again, the mouse is moving. It says, okay, I will stop executing the user program. I will see what user is trying to tell me through the mouse. Again, nothing. So that is a bad habit. Now, interrupt. One last thing about interrupt before we move forward. One more thing about interrupt is it could be external or internal. Now, external, you have found out that, external could be mouse click or, just I'm writing on Wacom board. So it's like, input coming from this board on which I'm writing with my electronic pen, or, there is HDMI through which I connected my monitor, or, I'm downloading something. So these are all external interrupt. And then there are internal interrupts. So what is an internal thing? Now, internal thing could be you have put some breakpoint. What is a breakpoint? So breakpoint is like when you're decoding a program. Remember your first C program which you were writing, or first few C programs you were writing, you would put a lot of printf statements because you want to see the intermediate results that, okay, this line, is it what kind of result it is giving? So once you get confidence, you stop writing too many printf statements in the middle, just to check what are your intermediate results so that you know whether the program is going or your logic is correct or not. So breakpoint are also something like, where you don't have to write printf statements yourself. It would do it itself. You just say on line 13 is important, put a breakpoint there, put a breakpoint next one. So it is important that, it will tell you the intermediate values. So that means program execution would stop at that particular point. The value would be displayed. If you okay that value, then program would go on. So that is known as a breakpoint. Second one would be some error, like divide by 0. Now this is a major error. If it is divide by 0, it would throw something which is known as exception. So exception is divide by 0 is an exception. It would say, okay, you can't go forward. I mean, this is not defined. Divide by 0 is a catastrophic error and your program execution has to stop. So these two words, normally interrupt is used for external events, whereas exception word is used for internal events, which is like internal to the program. So you have put a breakpoint in your program, or you have got divide by 0 error, or there are many other things which you would learn as we go forward in our ARM architecture class. So they are known as exceptions. So to sum it up, exceptions are due to internals of your program, user program, and interrupts are due to outside agencies like your mouse or keyboard, and whatever other terms we have defined. In this particular course, we will use the terms interrupt and exception interchangeably. I mean, I will call the whole thing as an interrupt, or I will call the thing as exception. Because the final exception, the final result, whether it is an interrupt or an exception, is that it will call something which is known as interrupt subroutine or exception subroutine. And that is a program which would tell you if you get an interrupt signal of a particular kind, say from keyboard, then these are the things you have to do. So you have to have a program for that. Similarly, for an exception, if it is divide by 0, that program is very simple. It would send a terminating signal to your message, and you will get some dirty message like your program abnormally terminated due to divide by 0 error. I mean, you will get that thing and program is terminated. But even for that, generating that simple signal and closing down your program, you have to have an exception. Suppose if you didn't have good interrupt or good exception, let's take a very simple case. If you don't have a good exception program written for divide by 0, what would happen? Your computer would hang because it wouldn't know what to do with divide by 0 because it is not defined. And if a program is not nicely written, which would terminate your current program and and tell the user that this particular program cannot go forward, and terminate the process. So that means now your processor is free to do other things. So exception handlers, and the program is known as handler, or interrupt handlers are very important. If you don't write good interrupt handler or exception handler, your processor would hang forever, and it would never come out. And some people, sometimes you may have seen it happens in your laptop, that your laptop freezes. So that means something like that must have happened inside, something which the exception handler writers or interrupt writers did not foresee that situation in your laptop. So only thing what is left with you is to hit the power switch or reset button. So you just turn off your computer and turn it on. Not a nice way to do, but that is not the final solution, and it is not a nice way to do. So finally, again, when we come back to the programmer's view, now you can understand that if you want to be a good programmer, if you want to write program in assembly language, you need to know what instructions are there, you need to know how many registers are there, and you need to know the interrupt model, that how do I send an interrupt. Finally, the fourth thing which I have written, memory architecture, is something I would like to tell you. And it is memory now you'll see that in a 32-bit processor. So what exactly do you mean by 32-bit processor? 32-bit processor means it can process a data which is 32-bit in length. So your operand 1 is 32-bit, operand 2 is 32-bit, and output is also a 32-bit. So that means it makes sense your memory has to be of 32-bit. It is not necessary that it is 32-bit, but if it is a 16-bit, then you have to make 2 trips to the memory to get one word, one instruction, or one data. So in a 32-bit processor, total addressable memory would be equal to 2 raised to 32. So you can, you have got, I can give you a simple example. I have got only 3 bits. With 3 bits, how many memory location I can address? I can say with 3 bits, I can address 2 raised to 3. That means 8 location. How? Well, I start from 000, 001, 010. I keep on going, and I will come to 110 and then 111. So 0 to 7 means total 8 things I can uniquely address. So similarly, if I've got 32-bit with me, then addressable memory would be 2 raised to 32-bit. So that is 4 GB. At this particular point, I want you to remember certain things, and this would come very helpful. 2 raised to 10 is 1K, right? 1 kilobyte. 2 raised to 20 is 1 meg, and 2 raised to 30 is 1 G. So if I say 2 raised to 32, how many bits it can do? So you say 2 raised to 32 is 2 raised to 2 times 2 raised to 30. So 2 raised to 2 is 4, and 2 raised to 30 is G. So it is 4 GB. Now, people who sell these boards, you will be practicing with these boards in your embedded hardware system. Nobody gives you full 4 GB memory. Now, you have 2 different problems. One is in laptop and one is in the small boards which might be used in your fridge or in your phone or in your washing machine. In In laptop, you say, okay, 4 GB is too less, I need 8 GB. Have you ever thought that, if your processor chip is 32-bit and addressable memory is only 4 GB, that means my maximum RAM size could be only 4 GB. How can you have 8 GB RAM or how can you have 16 GB RAM? I want you to think about it. Maybe search on the net and then, we will discuss. But as I tell you, the maximum physically addressable memory is 4 GB. I mean, that's a limit and it's a mathematical limit. You have got 32-bit number. So maximum addressable addresses which you can generate is 2 raised to 32, which is equal to 4 GB. Now, in laptop, you want more and more memory. You say 4 GB is too little. I want 8 GB. I want 16 GB, whatever. But in washing machine or your Arduino board or Raspberry Pi board, nobody is going to give you 4 GB, right? They may give you, and you can check the specs. You may have 256M, or for smaller board, it is size of K, such, you may have 64K of memory. You have got 32-bit processor and only 64K of memory. So what this means, someone asked a question, can you, repeat that just after a moment? So let me finish my thought that this is my addressable space, starting from 000, whatever, large number 32 zeros, to some number which says 4 GB. But the manufacturer is not going to give me 4 GB. So I say, okay, I will give a small slice over here. That's it. So normally, when we go to memory, you will realize that, there is a small boot sector over here, and then there is user memory and so on. But, forget about those things right now. They say, I can give you only this much memory, which is 64K. Now, when they do that, manufacturer does that, he has to give me memory map, that your memory would start from some number and end at some number. So if I don't know this, the program which I say store it in memory location something, using store instruction, that store the value of this register into particular memory location. Now, if I don't know about this fact, I may write this one, or I may write this one, this one, this one. And, the program will come back as memory location does not exist. Right? I'll get this message. Each manufacturer will give you 64K, 156K, 1 meg, 2 meg, whatever. But those numbers would be, some manufacturers may put their memory over here, someone may put their memory over here. So this is the reason why it is very important to know the memory map. Sometimes if you have written a program for a particular processor for, say, board which is produced by NXP, you wrote your program. You have written a program, your instruction set was known to you, your memory architecture, your interrupt model is also known to you, your register set is also known to you, but this thing is changing. Right? Your instruction set is remaining constant, your interrupts are remaining constant, and your register number is remaining constant, but this thing is changing. So if someone changes NXP processors and gives you Renesas, which is putting its memory over here between this number and this number, then your program will not run. So now you understand that why a programmer needs to know all 4 things, and that is known as programmer's view. We stop at this point, and from next class, we will start studying ARM architecture in earnest, right? Hopefully this Monday is not a holiday. So from coming Monday, we will start studying ARM architecture. Now, someone asked me a question. Can you repeat that question? Someone typed out a question. Can you just repeat it?
So Kadam is asking what happens when computer freezes?
Okay, so when computer freezes means it has got stuck somewhere and it does not know how to get out. So if you have written a good exception program or good interrupt handler or good exception handler, in such sticky situation, just like I told you, divide by 0. If I have not written good exception handler that how to stop everything, how to kill the process, and then comes out and tell the user that, okay, your program has been terminated and you can do something else. If that is not there, then what would happen is that your program does not know what to do. Your process is not killed. I mean, the word process you will study in your operating system, but that process hangs. And process hangs means that particular window is frozen if you're working in Linux. Or a Windows system is even bad, the whole window gets hanged. So that is what it means that my computer has frozen. That means inside some program has made a mistake, and that particular process, when I say program, it's also a process. It does not know how to get out of it. So it stands there waiting for some idea from the user. And that means things are not going to come out. So your computer freezes. So you have to manually reset it. Or that means hit the power button. Someone else also asked typed out another question. Can someone read it out to me?
Nishabd is asking, are cache memory and registers temporary memory storage?
Well, yes, in a way you are right. You can think of them as temporary memory storage. That those values are written and overwritten many number of times. Only thing, the last resort is your hard drive. If things are wiped out from the hard drive, then that particular program is lost. Just like you've written your C program, and if you delete it, then that program is gone. Whereas on the intermediate levels, your RAM and your cache, you don't even care, right? As a programmer, you don't care that I have put my program into hard drive. That's it. You don't care how many levels are there, what number of caches are there, what is the connection between your RAM and your L3 cache and L2 cache and L1 cache and register. That doesn't come in programmer's view. Okay, so we have studied programmer's view, and if you want to write good programs, then this is all you need. So in the first part, we are going to study programmer's view, and I took one lecture to make these terms very clear to you, so that you understand what I'm talking about from next lecture onwards. So okay, we stop here. Time is up. Thank you very much.
Hello, sir. I have a small doubt. In
Yes.
Snapdragon diagram, Snapdragon system diagram, it was written about Crate, CPU, Hexagon, DSP. So these are name of companies, or?
Yeah, see, Crate CPU is made by Qualcomm. Qualcomm is good in it. Adreno GPU is also made by them, and Hexagon DSP is also made by them. Qualcomm has got mastery in baseband because they've got lots of patents on CDMA. So I mean they own a lot of this, but Bluetooth is not their own. Wi-Fi is maybe someone else might be giving. Some of the display and LED might be coming from outside. So in a given SOC, even Apple does that. It makes some of the components, but others it is importing from some other company. So it is known as IPs. IPs are getting together, and you make a product. Some of the major companies like Sony, they do not manufacture each and every part. Most of the parts are outsourced. So this is what it is. So Crate is made by Qualcomm. Adreno is also Qualcomm, and Hexagon is also Qualcomm, and this is also baseband chip is Qualcomm. Others, it may be importing from outside.
Okay, thank you, sir.
Okay, someone asked, typed out another question regarding cache or something. I mean that. Okay, so we stop here. Maybe you can share it in the next class.